Standing standing wave will take, like standing wave.
Yes, standing wave I will take, but after this thermodynamics and KTG, right? I just need one more class to finish these two topics. Standing wave and KTG is a small topic. After completing KTG, I will come to standing wave.
Okay, okay, okay.
So right now we are just trying to complete adiabatic process. Ask Fazil to contact Nishkarsh once. Maybe he may be using the wrong ID. Adiabatic process. So adiabatic process means heat constant is constant. There is no heat can enter or leave the function system. The second thing about the adiabatic process is the walls should be non-conducting, perfectly, ideally insulating walls you should have. And the third thing is the process should be a very fast process. Next, we need equation for adiabatic process. Next, what we need is equation for adiabatic process. Equation for adiabatic process. Need an equation for a process to be adiabatic. So for adiabatic process, the equation is this. PV to the power gamma is equal to constant, the first equation. PV to the power gamma is equal to constant means P1 V1 to the power gamma is equal to P2 V2 to the power gamma. This is the first equation. Now, here gamma means gamma is the ratio of two specific heats of the gas. The ratio of specific heat at constant pressure and specific heat at constant volume. The ratio of two specific heat is gamma, that's Cp by C. In numericals, gamma would be given. In KTG, we will see how to derive gamma. Gamma would be given in numerical. So this is the relation between pressure and volume. You can have one more equation, and that is in between temperature and volume. The next equation could be in between temperature and volume. Because in adiabatic process, temperature is not constant. Adiabatic process, temperature is continuously changing. Volume is not constant. Volume is continuously changing. Also, the pressure is changing. So you will have few equations. One equation is connecting pressure and volume. Another equation can connect pressure and temperature. Another one can connect temperature and volume. So that's the first equation. The second equation is Tv to the power gamma minus 1 equal to constant. This equation is connecting temperature and volume. Tv to the power gamma minus 1 is constant. The next is T to the power 1 minus gamma. T to the power gamma is equal to constant. That's the third equation. So following are the three equations for adiabatic process. First is PV to the power gamma is constant. Second is the equation relating temperature and volume. And third one is the equation relating pressure and temperature. These are the three equations for adiabatic process. Okay, once you have equations of adiabatic process, you can calculate the expression of work done. In thermodynamics, the expression of work done is integral of PdV. Volume is from V1 to V2. Now for
Sir,
this P, yes,
can you show the previous slide?
yes, just a second. I have to go back. That's the first one, Fazil, the first equation.
Okay, sir. Thank you.
So this is work done. W is integral of PdV. For this P, you can use this equation. PV to the power gamma is constant. You can write here it's PV to the power gamma is equal to constant. So this is some constant is K. You can write that your P is its constant K divided by V to the power gamma. Because P is a variable. To integrate this P, I need a dP here. But instead of dP, this is dV here. So I cannot integrate it over here. So what I can do is, I can substitute P in terms of K and V to the power gamma. So when I do the substitution, I will get that work done is, its integral, it's V1 to V2. This is P. P I can write as K by V to the power gamma multiplied by D. Now what we can do is, we can take K outside. So we are left with V1 to V2. It's V to the power minus gamma D. Now, if I integrate this V to the power minus gamma, this comes out to be, this is K. This is V to the power minus gamma plus 1 divided by its minus gamma plus 1. And the limit is from V1 to V2. Next, what we can do is, work done is equal to K V to the power 1 minus gamma divided by 1 minus gamma, and the limit is from V1 to V2. Next, you can take this 1 minus gamma outside. So this is your work, that is K by 1 minus gamma. Then you can substitute limit. Instead of V, you can substitute V2. This is V2 to the power 1 minus gamma minus V1 to the power 1 minus gamma. So this is the expression of work done. K by 1 minus gamma. It's V2 to the power 1 minus gamma minus V1 to the power 1 minus gamma. Next, what? No, we don't leave this here. We can further solve it. Next, what we can do is, you can just multiply with this K. So this is K V2 to the power 1 minus gamma minus K V1 to the power 1 minus gamma divided by 1 minus gamma. Next, what we can do is, instead of this K, I can substitute P and V. So what we can do is, I can write P1 V1 to the power gamma is equal to P2 V2 to the power gamma, which is equal to K. So instead of this K, I can write P2 V2 as well as P1 V1. Yes, Noor, you don't need to derive these formulas. This equation of state for this adiabatic process is not a part of your syllabus. You don't need to derive these relations. But yes, the work done is important. You must derive the expression of work. So now not what we can do is, instead of this K, I can write P2 V2 to the power gamma. And instead of this K, I can write P1 V1 to the power gamma. So when I do this thing, instead of K, I'm writing P2 V2 to the power gamma into V2 to the power 1 minus gamma minus K. Instead of this K, I'm writing P1 V1 to the power gamma. It's V1 to the power 1 minus gamma divided by 1 minus gamma. So the work done is, it's P2 V2, it's gamma plus 1 minus gamma minus P1 V1 gamma plus 1 minus gamma divided by 1 minus gamma. So this gamma gets cancelled out with this gamma will cancel out with this gamma. This is P2 V2 minus P1 V1 over 1 minus gamma. This is the expression of work done. It's P2 V2 minus P1 V1 by 1 minus gamma. This is your work done. If you want, you can also convert this work done in terms of temperature. So what one can do is, you can just write this as PV is equal to nRT. So instead of this P1 V1, you can write nRT1 using ideal gas equation. And instead of this P2 V2, you can write nRT2. Now, if I do these substitutions here, your work done comes out to be, it's nRT2 minus nRT1 divided by 1 minus gamma. Next, what we can do is we can take this nr as constant. This is T2 minus T1 divided by 1 minus gamma. So this is the expression of work. So these are the two expressions of work done. You can either calculate your work done as P2V2 minus P1V1 by 1 minus gamma, or you can calculate your work done in this way. So these are the equations for adiabatic process. Just note it down, then we'll do few numericals on this concept. Okay, just tell me when you have written.
Done, sir.
Okay. Sania?
Yes, sir. Done. Done.
Done, sir.
So let's do few numericals on these relations. So the question says an ideal gas is compressed to half of its, don't take half, to 1/4 of its initial volume So if initially volume is V, so finally the volume becomes V by 4 at STP. So STP means your pressure, initial pressure is 1 atm and your initial temperature is like 300 Kelvin. Calculate first part, final pressure, second part, final temperature, and it is given that gamma is say 3 by 2. The value of gamma is 3 by 2. Okay, tell me one thing. If you are compressing the gas, then what change are you expecting in pressure? Pressure will remain same, it will increase, or you think it should decrease? Tell me.
So it will
If you are
increase.
compressing a gas, what change you expect in pressure? It will increase, right? If you are
Yes, sir.
compressing a gas, that means the pressure of the gas is increasing. So if the pressure of the gas is increasing, so see what you have. You have initial volume V. Sania, first part is very easy. So one by one, you all will solve. Okay, you are three here, na? So final pressure, final temperature, and work done. So everyone will solve one part. Sania, let's start from you. V1 is V. Initial volume is V, and it's saying that's compressing to 1/4 of initial volume. Sania, what should be the final volume? Sania, just open your mic. Initial volume is V, and it's saying the final volume is 1/4 of the initial volume. Then what's the final volume here? Sania, are you in class? Hmm. Final volume is V by 4. How much is P1? Yes, 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 yes. Sorry, I muted you. Sania, mic is open.
So yeah, now I can see.
So how much is P1? What is initial pressure?
180 p.
1 atm. Huh? We need final pressure. So you have
Yeah.
initial volume, you have final volume, you have initial pressure. You just have to calculate the final pressure. So out of these three equations, can you guess which one is the most appropriate equation? Out of this, and this equation, can you guess which one is the most appropriate one?
First one.
First one, very good. So we will use it like P1 V1 to the power gamma is equal to its P2 V2 to the power gamma. So you can calculate P2 from here. P2 is P1, it's V1 by V2 to the power gamma. This is P2. So how much is P1? P1 is 1 atm. P1 is 1 atm. How much is V1? V1 is V. How much is V2? V2 is V by 4. And how much is gamma? Gamma is 3 by 2 now. See, this is your gamma. This is equal to P2. Now, if I cancel this V with V, so what we are left with? We are left with 1 atm multiplied by its 4 to the power 3 by 2 is equal to P2. Now, to calculate this power 3 by 2, what we can do is, so it's just simply 1, huh? It's 1 into, remember this, the unit will be atm. So remember the unit will be atm only. So just it's 1 into 4 is 4. So it's 4 to the power 3 by 2. So what you can do is you write 4 to the power half, and this is cube of it, which is equal to P2. 4 to the power half is 2. Then you take cube of 2, which is equal to P2. Then you have 8 is equal to P2. So your P2 comes out to be 8 atm. Yes, everyone, tell me, is it clear? First part?
Yes, sir.
Sure. Fazal, next is your turn. I need final temperature. For final temperature, which equation is most appropriate? Out of these equations, which is most appropriate? Is there Fazal?
Sir, second one.
Second, yes. Because you have volume given, volume is given, you need temperature. So we will use second equation, which says T1 V1 to the power gamma minus 1 is T2 V2 to the power gamma minus 1. We need T2. So I can write T2 is T1 V1 by V2 to the power gamma minus 1. Now we can substitute the values over here. Huh? How much is T1? T1 is 300 Kelvin. Let's substitute these values here. T1 is 300. V1 is V. How much is V2? It's V by 4. So this 4 will come into denominator. Finally, it will come to numerator. So I'm not writing this step. I'm writing directly this 4 in numerator. Huh? I'm writing directly this 4 in numerator. To the power gamma minus 1, which is 3 by 2 minus 1 is equal to T2. We will cancel this V. This is 400. This is 4 to the power half is T2. So this is 300. 4 to the power half is 2, which is T2. So you have T2, which is 600 Kelvin. This is T2. So this is your final temperature, which is 600 Kelvin. Okay, third part. Noor, what expression will you prefer to calculate work done?
So P2 V2 minus P1 V1 divided by 1 minus gamma.
Okay, P2 V2. Why don't you use this expression? Wouldn't it would be easy? Because there's just T2, T1 and R, huh? So, okay,
Okay, sir.
we can use both the one. I'm using the temperature one. I find this is easier. NR T2 minus T1 by 1 minus gamma or gamma minus 1? It's 1 minus gamma. This is 1 minus gamma. So is there any information about the number of moles? Okay, no information about number of moles. So I'm taking 1 mole. an ideal gas, if there is no information about number of moles, I'm taking number of mole as 1. Just have 1 mole, n equal to 1. Your gas constant is 8.314 joule per kg per Kelvin. Your T1 is 300 Kelvin, and we just have calculated that T2 is 600 Kelvin, and your gamma is 3 by 2, which is equal to 1.5. If I substitute these values here, it's N, which is 1, gas constant R, which is 8.314, it's T2 minus T1, which is 600 minus 300 by 1 minus gamma, which is 1.5. So work done comes out to be it's 8.314 into 300 divided by 0.5. This much of joule is your work done. It's coming with a negative sign. Since gas, you are compressing the gas. When you compress the gas, it's work done on the gas, which is negative. Tell me if you have doubt in any of the part.
Sir, finish.
Yes, certain.
Yes, sir.
Yes, sir.
Okay. Now, after this question, if I apply, say, adiabatic process, first law of thermodynamics for adiabatic process. First law of thermodynamics for adiabatic process. Adiabatic process. So from here, what we can conclude is, we know that there is no change in heat. Delta Q is 0. So delta Q is, it's delta U plus delta W. If I substitute delta Q equal to 0 here, then this is delta U plus delta W. We will say that delta U is minus of delta W. Delta U is minus delta W means if delta W is positive. Delta W is positive means your gas is expanding. That means your delta U is negative. Delta U is negative means internal energy is decreasing. If internal energy is decreasing, that means temperature is decreasing. And similarly, if your delta W is negative, if I write that delta W is negative, means your gas is compressing. You're compressing the gas. Your delta U will be positive now because it's negative of negative. Delta U is positive means it's increasing. Delta U increases, internal energy increases. That means you can say that temperature increases. Temperature increases. That's the first law of thermodynamics for an adiabatic process. Okay, just note it down. Then we do the next thing.
Done, sir.
After adiabatic process, the next is, so we have done isothermal process, we did adiabatic process, the next is isochoric process. So there is no separate equation for isochoric process. Isochoric process means your volume is constant. Volume is constant, that means change in volume is zero. The volume is not changing. So all processes which are at constant volume are isochoric. You can say that work done, which is equal to pressure into change in volume, is zero. So in isochoric process, work done is zero. That's it. There is no separate equation of state. For isochoric process, we use equation of ideal gas. Similarly, you have one more process which is known as isobaric. And again, there is no separate special equation of state for isobaric process. We use the ideal gas equation. Here, pressure is constant. Pressure is constant. Change in pressure is zero. That's your isobaric process. That's it. So this was about process. Then after process, we have some limitations of first law of thermodynamics, and then we'll see the statements of second law. The heat engine, the Carnot cycle, the refrigerator is not a part of syllabus now. But if you have done that in class, I will be discussing it. Have you done that heat engine, Carnot
No, sir.
cycle, and refrigerator in your class? No.
No, sir.
Okay, that
No,
means
sir.
we just, yes or no? No.
No, sir. No.
Right. Let's just note it down. I need just 5 more minutes to complete this.
Done, sir.
Okay. The next is limitations of first law of thermodynamics. The next is limitation of first law of thermodynamics. First law of thermodynamics. Limitation of first law of thermodynamics. The first limitation is it does not tell you about the direction of transfer of heat. Means according to first law of thermodynamics, heat can transfer from a hot body to a cold body, and it can as well transfer from a cold body to hot body. It gives no idea about the direction of transfer of heat. So the first limitation is it does not indicate the direction of heat transfer. What all it says is that energy should remain conserved. Means if you have a body at 100 degrees Celsius and you have a body at 10 degrees Celsius, if 10 joule of energy is moving from this body to this body, energy is conserved. This one is losing heat and this one is gaining heat. But even if energy transfer from 10 to 100, is 10 joule of energy is transferring from a body at 10 degrees Celsius to a body at 100 degrees Celsius. It's again gaining energy. Energy is transferring. That's it. It's again, the energy is again conserved. But you know by your experience that energy cannot transfer from lower to higher temperature. It always transfers from higher to lower temperature. So it does give no idea about the direction of transfer of heat. Second, it does not tell about the condition under which heat can be converted into mechanical work. Heat can be converted into mechanical work. So it does not tell you about the conditions under which heat can be converted into mechanical work done. This means if you have a heat engine, right? What happened in a heat engine? The petrol or the fuel burns, and the heat energy of the fuel get converted into mechanical energy. If you take the case of a car, in a car, if you take a petrol engine, then petrol burns. That heat energy will rotate the wheel of the car. This is what the heat engine is doing. So first law of thermodynamics says in any condition, heat can be converted into work done. But not every heat can be converted into work done. When a petrol burns, this heat energy is converting into work done. But when a car moves, it gets heated up. It gets heated up, its body gets heated up. That heat energy cannot be converted into useful work done. Not every energy, heat energy, can be converted into work done. So first law does not tell you about under which direction your heat energy is converting into mechanical work done. And it also does not tell you the extent of heat transfer. It does not tell about the extent to which heat transfer. Or heat convert into work done. Like according to this law, 100% of heat energy can be converted into work done. But the experiment says you cannot convert 100% of heat energy into work done. A major part or a big part of energy will get dissipated in the form of heat. So these are some limitations of first law of thermodynamics. So to remove these limitations, we have second law of thermodynamics. We have second law of thermodynamics. Now, this second law of thermodynamics have two statements. The first is the statement of Kelvin and Planck. The first one is Kelvin-Planck statement. Kelvin-Planck statement. This Kelvin-Planck statement says it is impossible to construct an engine these all are just statements. The equations are not a part of syllabus. So second, which will produce no effect other than extracting heat from reservoir and performing an equivalent amount of work. And performing an equivalent amount of work. That's Kelvin-Planck statement. In short, this statement says efficiency of engine can never be 100%. It says that efficiency of engine cannot be 100%. Means you can't have an engine having 100% efficiency. The second is the statement of Clausius. Clausius statement. Clausius statement. This statement is basically rectify this problem. This problem. This says that heat cannot transfer from lower to higher temperature. It can transfer from higher to lower temperature only. So this says it is impossible for a self-acting machine unaided by any external agency to transfer heat from lower to higher temperature. Lower to higher temperature. If you want to transfer heat from a body at lower temperature to a body at high temperature, you would need an external agency. The one example of the device which transfer heat from low to high temperature is your AC, air conditioner, refrigerator. It transfer heat from low to high temperature. But all refrigerators, all air conditions need some external force. They need some external agency which can transfer heat from lower to high temperature. Transfer heat from lower to high temperature. Okay, just note it down. That's about thermodynamics. Next, we will start with kinetic theory of gas. Just tell me when you have written these definitions.
Done, sir.
Okay.
Done, sir.
So that was all about thermodynamics. After this, the topics are heat engine, Carnot cycle, and refrigerator. So these are not a part of syllabus this year. Just note it down. Then we'll start with the KTG, kinetic theory of gas.
Done, sir.
Yes, sir. I'm sir.
Sanya? Yes, Sanya, have written?
Yes, sir.
Okay, so that was about thermodynamics. The next is kinetic theory of gas. The next topic is kinetic theory of gas. See, what we do in kinetic theory of gas, in kinetic theory of gas, we try to derive the macroscopic properties of gas from the kinetic energy. So I am describing some macroscopic properties of gas, few macroscopic properties of gas. The macroscopic properties of gas are volume, its pressure, its temperature. So what we do in kinetic theory is, in kinetic theory of gas, we try to derive this expression of pressure, this expression of temperature from the kinetic energy of gas molecule. This is what we will do in kinetic theory of gas. It's a very interesting topic. Just using the kinetic energy, the motion of gas molecules, you will derive the expressions of pressure, you will derive the expression of temperature, and all gas laws that you must have studied in chemistry. So the introduction of this chapter says, in KTG, kinetic theory of gas, we derive macroscopic properties from kinetic energy of gas molecules. That's why the name is kinetic theory of gas. Kinetic energy of gas molecules. So using kinetic energy of gas molecules, we will derive these things. Basically, temperature comes from the kinetic energy of molecules. Pressure of gas is the result of kinetic energy of molecules. So we will try to find a relation between pressure and kinetic energy, temperature and kinetic energy. That's KTG. Okay, just note it down. Then we will write some assumptions for a gas to be an ideal.
Done, sir.
So this kinetic theory of gas, KTG, starts with certain assumptions. It starts with certain assumptions. This KTG starts with certain assumptions. The first assumption is gas molecules. I'm not writing all assumptions. I'm writing just 3 of them, which I will use in the next derivation. The rest I will send in the form of a PDF. Gas molecules are rigid elastic spheres identical in all respect. Identical in all respect. So this is assumptions for kinetic theory of an ideal gas. This is assumptions for kinetic theory of an ideal gas. So in this, we will consider that your gas is ideal. Whatever we will derive in this section, we will assume that the given gas is ideal. And if the gas is ideal, then what approximations, what assumptions we will use? The first one. The gas molecules are rigid elastic spheres, identical in all respect. Means if you take hydrogen, all molecules of hydrogen are identical. Second assumption. Size of molecule is negligible compared to average distance between molecules. So the size is very, very small. If you compare with the distance between individual molecules, the size is negligible. So we will not consider the size of gas molecules in our calculation. So these molecules are in state of random motion. So during random motion, these molecules collide with one another and with walls of container. So the molecules collide with one another and with the walls of container. And this collision is elastic. This collision is elastic. There is no change in kinetic energy. The collision is perfectly elastic. So these are some assumptions for the kinetic energy of an ideal gas. They are elastic and rigid spheres. The size is negligible. And the last one, the collision is elastic collision. On the basis of these assumptions, we will try to derive an expression for pressure exerted by gas in terms of velocity. Just note it down, then we'll derive the expression. Just tell me once you have written these assumptions.
Done, sir.
Okay. The next is the expression for pressure exerted by gas. Expression for pressure exerted by gas. So this is the most important calculation in KTG. Using the velocity of gas molecules, you will derive the actual expression for pressure. Expression for the pressure exerted by gas. See how we do it. So I take a box. You can say this is a glass container. In this glass container, I filled an ideal gas, and the molecules of ideal gas are moving. These molecules, this is molecules of ideal gas. This is glass chamber. Glass vessel. These are molecules of ideal gas. So these molecules are moving and they are colliding with the wall of the vessel. They collide with the wall of vessel and rebound. When these molecules collide with the wall of the vessel, these molecules are actually exerting force over the wall of vessel. And that force per unit area is the pressure exerted by gas molecules. Simple. Logically, it's a simple thing. See, you have various molecules, gas molecules inside the vessel. These molecules are moving, they collide with the wall and rebound. When these molecules collide with the wall, they're exerting some force over the wall. That force per unit area is pressure. That's it. This is the expression for pressure exerted by the ideal gas. Now we have to calculate this pressure. So let's consider a single gas molecule. So in this system, you have number of gas molecules. Let's start with a single gas molecules. So I'm defining some terms. N are the number of molecules per unit volume. Number of gas molecules per unit volume. Number of gas molecules per unit volume. Then you have A, which is the area of cross section. This is the area. This is the area of the wall. A is the area of wall. Then I'm defining the mass of each molecule as M. M is mass of each molecule. Mass of each molecule. The mass of each molecule is smaller. This each molecule of mass M, it's moving with certain velocity. Just for the sake of simplicity, I am considering that the velocity of the molecule is Vx. So Vx is velocity of gas molecules along x-axis. Gas molecules along x-axis. So this is your gas molecule. This is colliding with this thing with a velocity Vx. Since the collision is elastic, so it will rebound with the same velocity, just its direction will reverse. So when gas molecule collide with the wall of vessel, it rebounds. Its velocity, it rebounds. It becomes minus Vx. Its velocity is minus Vx. Minus of Vx. This negative sign simply shows that the direction is changing. Now I need change in momentum of the molecule. See, initial velocity is Vx, final velocity is minus Vx. Sania, what is momentum? If mass and velocity are given, how would you calculate the momentum of gas molecule? Sania, the mass of gas molecule is m, velocity is Vx. What is the momentum of gas molecules?
M into Vx.
M into
No,
V.
no.
Yes,
Yeah.
yes, m into V. But I don't need momentum. I need change in momentum of gas molecules. Change in momentum of gas molecules.
P.
Let's write this as delta P, okay?
Yeah.
This change is along x-axis. Now, how would you calculate change? It will be initial minus final or final minus initial? Yes. Yes, Anya. Is it initial minus final or final minus initial?
Initial minus final.
Change is final momentum minus initial momentum. Okay, now tell me, how much is the final momentum of the gas molecule? The mass of gas molecule is m and its velocity is minus Vx. What's the final momentum? First, Anya, we have to finish this thing today.
Minus Vx.
Minus mvx, right?
Mvx, yeah.
And what is the initial momentum? Mass is m and velocity is Vx. How much is the initial momentum?
Mvx.
Great. So how much is this now?
M minus M bracket.
Yeah,
Vx.
minus 2 mvx. Can I write? It's minus mvx,
Yeah.
minus. That is the change in the molecule, change in the momentum of molecule. Now, can you guess? This is the change in the momentum of molecule. Now I need change in momentum of wall because you are exerting some force over the wall. Can you guess how much is the change in momentum of wall? Fazil. This is the change in the momentum of gas molecule. Collision is perfectly elastic. Can you guess the change in the momentum of wall? Fazil.
Yes, sir.
How much is the change in the momentum of wall?
Sir, is it 0?
No, 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 no. Because when this molecule is striking the wall, the momentum of the wall is changing. You can use Newton's third law. Newton's third law says for action and reaction, if you take one force as positive, then another is negative. And this change in momentum is related to force. You can say that change in momentum of wall is negative of minus of 2 mvx. I'm taking one more negative here, so it becomes 2 mvx. Remember, this is through Newton's third law. Because Newton's third law tells that force have action and reaction pair. And force is nothing but change in momentum by time. So whatever Newton's third law says about force, I convert that in terms of momentum. So this is the change in momentum of wall. I call this as equation number 1. So when is this change in momentum? When one molecule is striking the wall of the container. So now pay attention for the next few steps, they are crucial. So when one molecule strike the wall of container, change in momentum of wall change in momentum is twice of change in momentum of wall. of wall is twice of mvx. Okay, tell me one thing. This is when one gas molecule is striking. If you have n gas molecules, when n gas molecule strike the wall, of container. Yes, Noor, can you guess the change in momentum?
Yes, sir.
Yes, Noor. Can you guess the change in momentum when n gas molecules are striking the wall?
N time, N into 2M.
Yes, it will be n into its 2m Vx. I call this as equation number 2. But this capital N is not given. You're supposed to calculate this capital N in terms of small n, the area of the wall, and the time taken. So I'm defining capital N here. Capital N is the number of gas molecules. It's a very lengthy derivation. The number of gas molecules striking the wall in time delta t. So I need the number of gas molecules which are striking the wall in time delta t. So for this total number of molecules, what we can do is we can take number of molecules per unit volume, and we can multiply this, the volume occupied by gas molecules in time delta. This is unitary method simply. Total number of molecules is number of molecules per unit volume multiplied the volume occupied by gas molecules in time delta t. Now the task is to calculate somehow this volume occupied by gas molecules in a time delta t. So let's name this equation something. Let's name this as 3. Okay. So to calculate the volume, see, you can do this simple calculation. The molecules are traveling with a speed Vx. So the distance that these molecules will travel in time delta t is Vx into delta t. Okay, if you know this distance, Sania, can you tell me how much is this area? This whole area. If you know this distance, you know the area of cross section is A. Then can you tell me the wall? How much is the volume of this much volume that I have shaded with the red color? Try, Sania.
MA.
What again?
Sir, I don't know.
You don't know. Fazil, will you try? How much is this volume if you have area and this length?
Sir, A minus 1.
Noor, will you try?
So Vx delta T into A.
Yeah. Volume is area multiplied by length. That's volume. So if I need the volume of this much of section, so what I can do is I will take the area of the section and multiply it by the length. This is how you calculate the volume of a cylinder, right? You write volume of a cylinder as pi r square L. Pi r square is the area and L is the length. So that is the volume of the cylinder. So volume occupied by gas molecules in time delta t, volume occupied by gas molecule in time delta t is area of cross section multiplied by the distance that gas molecules have traveled. See, distance is speed into time. So this is the volume A into Vx into delta t. This is equation number 4. I'm not writing. I will use one more thing here. Is it clear? Just tell me, is it clear now?
Yes, sir.
this volume.
Yes, sir.
If I substitute 4 in 3, you know that number of molecules per unit volume is basically your small m. It will comes out to be that this is small m multiplied by a Vx multiplied by delta T, that is capital N, it's N into this volume, a Vx into delta T. There is one more thing left, and that thing is, see, if you have 1000 molecules in this region, I'm saying let's assume you have 1000 molecules in this region. Now use your logic and tell me, are all 1000 molecules are going to strike the wall of the container? Are all are striking at the same time, or some are coming after striking the wall? I'm repeating it again. Say you have 1000 molecules in the container. Is it so that all 1000 molecules will strike the wall at one instant? Let's say I ask you to observe this at t equal to 2 p.m. What you will observe are all molecules are going to strike the wall of the container, or few molecules are going to strike the wall of the container and that rest are rebounding.
Sir, few molecules.
Few molecules. So few molecules will strike the wall and others will rebound. When the molecules are traveling, few will strike the wall and others will rebound. So if you have 1000 molecules, then you can say out of 1000 molecules, roughly 50% molecules are going to strike the wall and 50% are coming after striking the wall. So when at a particular instant you look at the wall, only 50% molecules are striking, the rest are rebounding after striking the wall. Are you getting this thing?
Sir, could you explain again?
Yeah. Say you have 1000 molecules here. This region is filled with 1000 molecules. And I ask you to calculate or to count the number of molecules which are striking the wall at any time instant. Let's say I'm asking you to calculate it at 2 p.m. When you look at this wall at 2 p.m., what you will observe is, you will observe that few molecules are striking the wall and there are few molecules which are rebounding. You will get two types of molecules, one which is striking and others which are rebounding. When I say to count only those molecules which are striking the wall, then you would say, okay, roughly 50% are striking and the rest are rebounding. This is what I'm saying. If you have total 1000 molecules, then 500 are striking and other are rebounding after striking the wall. Yes, Fazil.
Understood, sir.
Okay. So this 50% is just due to probability. So I'm just saying that the chances are equal, means equal number of, there are equal chances that molecules are striking and rebounding. So I would say the number of molecules which are striking the wall at any time is just half of this. I'm using a factor of half here, this factor of half. This is just due to the fact that few are striking the wall and other are moving after striking. So I'm writing this thing in statement. On the average, half of such molecules are moving towards the wall and other half away from the wall. Away from the wall. That's why I'm taking this factor of half here. Now, if I substitute this 5 here, then I can calculate the total change in the momentum of wall. So change in So what we can do is, I'm just substituting this equation number 5 here in 2. So if I substitute 5 in 2, then what we will get is change in momentum of wall. Change in momentum of wall. The change in momentum of wall is, instead of this n, I will substitute this term half n a Vx into delta T. These are basically the number of molecules multiplied by 2m Vx. This delta T, right? Delta T. This 2 will cancel this 2. So the change in the momentum of wall is, it's NA m Vx square multiplied by delta T. This is the change in the momentum of the wall. Now, once you have the change in momentum, you can calculate force. Sania, if you have change in momentum, do you remember Newton's second law to calculate force?
F is equal to ma.
Ma. Else than ma, change in terms force in terms of change in momentum. Any other formula? Any other formula? Newton's second law says that force is rate of change of momentum, change in momentum by time interval. So if I substitute these values here, then your force comes out to be NAM Vx square delta T divided by delta T. So this gets cancelled out. So the force on the wall is this. It's NAM Vx square. Next thing. Fazil, now I got the expression of force. Force exerted by molecules on the wall of the container. Now, can you tell me that how do you calculate pressure? How to calculate pressure on the wall?
Sir, force by area.
Force by area. Very good. So pressure acting on the wall, we represent it by P. Pressure is force upon area. It's NAM Vx square divided by area. It gets cancelled out, which is NM Vx square. So this is the expression of pressure, which is Nm Vx square. There is just one small issue here. I call this as equation number 6. Not yet completed. There is one issue. Okay, tell me just one thing. In a container, are all gas molecules moving with the same speed? What do you think? In a container, are all gas molecules moving with the same speed?
No, sir.
So what would be better, to take the velocity of a single molecule or take the average of all molecules?
Average.
The better way is to take average, huh? As all molecules move with different velocities, they all move with different velocities. So we will replace Vx square by Vx square average. I'm taking the average of it. This is average value. Huh? So if I do this substitution, instead of this Vx square, I'm taking just the average. So the expression of force is Nm Vx square average. This is the thing. There is one more issue. Is it correct to assume that gas molecules are moving only along x-axis, or they can move in any direction?
So they can move in any direction.
They can move in any direction. They can move either x-axis or along y-axis or along z-axis. So again, this is not a correct assumption to take that molecules are traveling only along x-axis. What one should take is, one should consider that molecule can move along y-axis or z-axis in any direction. So the gas molecule, the gas is isotropic. Isotropic means it can travel in any direction. It has same probability to travel along x-axis or y-axis or z-axis. So what we can say is, so the molecular velocities are almost equally distributed in different directions. So by symmetry, so the total velocity of gas molecule, total velocity of gas molecule V is Vx I cap plus Vy j cap plus Vz k cap. Now, if you wish to calculate the magnitude of V, then from basic vectors, you know that this is Vx square, Vy square plus Vz square. If I take V square, then this V square is, if I'm taking square on both the sides, this is Vx square, Vy square plus Vz square. I'm taking the average, okay? The average of all velocities. So I'm taking all average velocities. V square bar is Vx square bar plus Vy square bar plus Vz square bar. Next, what we can do is Vx square bar is equal to Vy square bar is equal to, now I'm taking the symmetry argument. I'm saying that gas molecules have equal probability to move in any directions. That means by symmetry, it has same average velocity along x-axis, same average velocity along y-axis, same average velocity along z-axis. By saying that they have same average velocity along x, y, and z simply means that they have same probability to travel along x, y, and z axis. So this is Vx square is Vy square is equal to Vz square. I can substitute all these things here. When I do this substitution, instead of Vy square, I'm writing Vx square. Instead of Vz square, I'm writing Vx square. When I do all these substitutions, what I will get is, I will get V square bar is equal to 3 Vx square bar. I can write Vx square bar is equal to V square bar divided by 3. So I call this expression, this 6, this is 7th. So instead of this thing, I'm just substituting. This is the total velocity of gas molecule. This was wrong assumption. In equation 7, I was assuming that gas molecules are traveling only along x-axis. They have equal probability to travel in any direction. When you take that probability, you got this equation. This is equation number 8. Now, if you substitute 8 and 7, you will get the expression of pressure is, it's Nm V square by 3. So this is the expression of pressure exerted by gas molecules, 1 by 3 Nm V square. So this is pressure exerted by gas molecules, 1 by 3 nm v square bar. That's an important calculation from kinetic theory of gas. Just note it down, then we'll convert this expression into many forms. And tell me when you have written it. Huh?
Done, sir.
Fazil, Noor, can I change the slide?
Yes, sir, done.
Yes, sir. Done, sir.
Yes, sir. Done.
Yes, written.
Yes, sir.
Sir. Yes, sir. Done.
Done, sir.
So this is the expression of pressure exerted by gas. So if you look at the last expression carefully, the pressure depends on velocity. N is number of gas molecules basically. M is the mass of gas molecules and V is velocity. So that is the kinetic theory of gas. You have derived pressure in terms of the velocity of molecules. You can express this thing into many form. Like the expression of pressure is 1 by 3, it's N into M into V square bar. So what is N? N is number of molecules per unit volume. Number density, number of molecules per unit volume. What you can do is you can write this small n as capital N by V. N is total number of molecules. Total number of molecules. And V is the volume of gas. So if I make this substitution over here, let's name this equation. The name of the equation is, this should be equation number 9, right? That's equation number 9. Let's name this as equation number 9. Let's name this as equation number 10. If I substitute 10 in 9, what I will get is P is 1 by 3 N, which is number of molecules divided by volume into M into V square bar. Now, what was small m? Small m is the molecule mass of one molecule. Small m is mass of one molecule. But instead of this, if I take N into M, it's capital M is mass of gas, whole gas of all molecules. So if I make this substitution instead of NV, if I'm substituting capital M, what I get is pressure is 1 by 3 M into V bar square divided by volume. And you can write your mass by volume as density. So what I get is the pressure is in terms of density of gas, 1 by 3 V square bar. This is the expression of pressure in terms of the density of the gas. It's 1 by 3 rho V square bar. You can do one more thing. If you want, you can convert this in terms of kinetic energy. To convert this in terms of kinetic energy, what simply you can do is just multiply and divide by 2. That's it. So I can write this as this is 2 by 3. It's 1 by 2 rho V square bar. You know that kinetic energy is half mv square. But if I take kinetic energy per unit volume, this we have done in fluid mechanics, then per unit volume is m by volume, mass by volume is density. So this can be written as it's half rho V square bar can be written as kinetic energy per unit volume. So that is the relation between pressure and kinetic energy per unit volume. You can say that your pressure is 2 by 3 times kinetic energy per unit volume. That's the pressure of the gas. It's 2 by 3 times the kinetic energy per unit volume. So this is how you can connect the pressure of the gas and the kinetic energy. Just note it down, then we will try to connect this with the temperature. Just tell me when you have written. Huh?
Done, sir.
Okay.
Yes, sir. Done.
Next, what we can do is we can connect this thing with the temperature. Next, we have to express this expression in terms of temperature. And that expression is what we call kinetic interpretation of temperature. Kinetic interpretation of temperature. So kinetic interpretation of temperature means we are trying to connect the kinetic energy of gas with the temperature. So if I use this equation, I name this as equation number 11. From 11. What is 11? 11 is P is equal to 2 by 3 K per unit volume. 2 by 3 kinetic energy per unit volume. So I can write this kinetic energy per unit volume as this is 2 by 3. I write this as kinetic energy divided by volume and multiply with V here. So what I get is it's PV is equal to 2 by 3 of kinetic energy. I call this as equation number 12. What next I can do is I can use ideal gas equation using ideal gas equation for 1 mole. For 1 mole of gas. Now, if I use ideal gas equation for 1 mole, then I can write PV is equal to, usually PV is equal to nRT, but for 1 mole your N is 1, PV is equal to RT. That is equation number 13. If I substitute 13 in 12, On substituting 13 in 12, what I get is RT is 2 by 3 kinetic energy. That is the relation between kinetic energy and temperature. That kinetic energy is 3 by 2 RT. This is relation between kinetic energy and temperature. Now, this is kinetic energy for n molecules. If you want, this is kinetic energy of n gas molecules. But if you need kinetic energy of one gas molecule, what we can do is we can just divide this kinetic energy by n, and here it will be 3 by 2 RT by n. This R by n basically is known as, and n is Avogadro number, okay? R by n is another constant which is known as Boltzmann constant. Another constant which is known as Boltzmann constant. Now, if I do these substitutions, instead of this R by n, I am using Kb. So you can say that kinetic energy per molecule, I am writing it as K, is 3 by 2 kBd. This R by n is Boltzmann constant. So you can write this as 3 by 2 Boltzmann constant into temperature. That's kinetic energy per molecule. Just note it down.
That's it.
Okay. Yes, everyone written?
Yes, sir. Done.
Done, sir.
Okay.
I'm
The
done, sir.
next is, yes. You won't get many numericals from this thing. You will get conceptual questions from here. I'm coming to conceptual questions, but first I want to discuss some type of velocities of a gas. So the next section is average, root mean, and most probable speed. Average, root mean square, and then the last is most probable speed. Say if you take a vessel or some sort of container and you fill that container or that vessel with gas molecules, then in that container all molecules have different velocities. Like if I take this container, I fill this container with some sort of gas, huh? So all molecules will have different velocities here. They all are moving with different velocities. This is V1, this is V2, this is V3, this is V4, this is V5. So if I say, what is the velocity of gas? Since all molecules have different velocities, so what you will say is you will tell me the average velocity of the gas. You will take average of all and you will say this is the average velocity. There are many methods to take average. One average is average that you know, add them up and divide it by the number of velocities. Another interesting type of average is root mean square, and the last one is most probable speed. Let's say first see what do you mean by average. Average speed. Average speed is just the arithmetic mean of the speeds of gas molecules. Average speed is just the arithmetic mean arithmetic mean of speed of gas molecules. If you're just taking the arithmetic mean of the speed of gas molecules, then that is the average speed. It's simple. How do we calculate average? Just add them up. You just add them up. You add up all velocities up to n and you divide it by n. That's the average velocity. Now, you can also derive this average velocity in terms of gas constant, but I'm not doing that derivation. That derivation is not a part of your syllabus. But just like we have derived this expression here, this expression here. In the same way, you can derive the expression from this expression, you can derive the expression for the average speed. So I'm just writing that expression directly. No need to derive that expression. So that is 8RT by pi m. Or you can write this as, this is 8 kBt by pi m. Remember the difference between capital M and small m. Capital M is molar mass of 1 mole. And this is mass of 1 molecule. Mass of 1 molecule. You should always remember the relation between them. Molar mass is Avogadro number multiplied by small m. This is Avogadro number. This is Avogadro number. This is average speed. Okay, just note it down. Then we'll do root mean square and then the most probable speed. Just note it down. Then we'll write the root mean square, RMS. Just note it down and tell me when you have written. Huh?
Done, sir.
Okay. Next is RMS. Root mean square speed. Root mean square speed. This is again a type of average, but a different type of average. Root mean square. While doing root mean square, what we do is we first take square, then we take mean, then we take root. So we write RMS in this way. V RMS is, we first take square, V1 square, V2 square, V3 square, Vn square. Then we take mean. For mean, just add them up and divide it by the number. Then we take root. That's the RMS. This is how we take RMS velocity of gas molecules. And the most commonly used velocity is the RMS velocity or the RMS speed. Whenever in a question he talk about the speed of gas, means he's saying RMS speed. By default, speed of gas is RMS. This is it. And if you want to convert this VRMS in terms of temperature, then the expression is it's either 3RT by capital M or is this 3RT, not 3RT, 3 kBT I should write. 3 kBT by small m. Sanya, what is difference between capital M and small m?
Small m is number of moles and capital N is Newton.
Capital M is?
Newton.
Read this. What is capital M?
Molar mass, sorry.
And what is small m?
Mass of one molecule.
Okay, now tell me what is capital M? Yes, yes. What is capital M? Just tell me once more.
Sir, you was asking capital N or M?
M, M, M.
M, okay. Molar mass.
And this?
and this is molecule.
Mass
Mass.
of one molecule.
One
Remember
molecule.
this always. So most probable speed means speed which is carried by the maximum number of molecules. Say you have 5 molecules of gas. Molecule number 1 have a speed 100, molecule number 2 have 10, molecule number 3 had 90, 4 had 100, 5 had 100. So this velocity is carried by maximum number of molecules. So we call this as most probable. Most probable means velocity which is carried by maximum number of molecules. So most probable speed means speed possessed by maximum number of molecules in a gas. So the speed possessed by the maximum number of molecules in the gas is most probable speed. And we write the most probable speed as root over twice of kBt by m, or you can write this as root over 2RT by m. 2RT by m. That's most probable speed. So these are the 3 types of speed that a gas molecule can have: average, RMS, and most probable. Just note it down and tell me which one is the greatest out of these 3. Out of these 3, just tell me which one is the greatest. Okay. Just tell me out of these 3 speed, which one have the maximum value?
Second
Which?
one.
So VRMS.
Okay, very good. So the maximum is VRMS. See if you compare them. This is root 3, fine. This is root 2, and this is root 8 by pi. Root 8 by pi means it's 8 by 3.14. So this VRMS is the maximum. Then you have this V average. And the minimum is V most probable speed. That's it. Always remember this relation is a 1-marker question. So this is clear for everyone. Huh?
Yes, sir.
Yes, sir.
Okay, so let's stop here. We'll can we have one class tomorrow at 3 p.m. as per your time? I'll finish this thing tomorrow. Just 1 hour class.
Okay, sir. Sir,
Noor and
3
Fazil.
to what?
3 to 4:30.
Okay.
Fazil, tomorrow I will finish this thing. Or maybe tomorrow I will start. Okay,
Yes, sir.
okay. Do have an issue. Do have issue. Okay. So when is your exam? Your exam is on 10th.
11.
Physics exam is on
Physics is
11th.
on 15th.
Sorry.
Okay, it's starting
15th.
from 11th. Huh? I need just 2 more classes to finish this thing up. So you can keep those classes. One is on Thursday. Can we take one class on Friday morning? Huh? This we can do. Noor?
Okay, sir. No
Okay,
problem.
sir.
So okay, don't take class tomorrow. We keep one class on Thursday and then next on Friday. So Friday I will finish the syllabus. Huh?
Okay, sir.
Sure. Okay, bye.
Okay. Thank you, sir.
Sure.
Thank you, sir.